So go ahead and take a minute to get out your Chapter 6 notes or PowerPoints. All right, so Chapter 6 is our energy chapter. So this is called thermodynamics. It's the study of chemistry and energy. And we touched on it a little bit in our first chapter. We saw the exploding gummy bear. And so here we're going to go more in depth into thermodynamics. And first off, we're going to be talking about energy. And energy is the capacity to do work or transfer heat. Work we can think of as energy used to cause an object with mass to move against force. But the last definition here is the one we're going to use the most, and that says heat is the energy used to cause the temperature of an object to increase. And this is probably the one that you're most familiar with anyways. So that's the one we're going to be using the most here. But any questions on anything so far? All right, so now we have to talk about our units of energy. And the most common one, the one that you see all the time on food packages, is calories. So calories really are units of energy. So when you're looking at the back of your favorite candy bar or your gummy bears and you're like, oh man, there's like 300 calories in here. You might be like, oh yay, there's 300 of units of energy in here. I'm gonna have so much energy. So a calorie really is a unit of energy. When we eat food, we're taking energy into our bodies. When you eat gummy bears, you're just taking a lot of energy into your body. All right, so the amount of energy needed to raise 1 gram of water by 1 degree Celsius. That is the official definition of a calorie. However, we have an SI unit of energy called the joule. We'll talk a little bit about calories, but we're going to focus more on the joule as our energy unit. I do want you to know conversion factors on the bottom, and specifically the ones I want you to know, the ones in blue. So 1 calorie, lowercase c, is 4.184 joules. So that's a very important one. They're all important, but this was probably the most important of the ones that we're going to see. The next one says that 1 calorie with a capital C is equal to 1 kilocalorie. So on your food packages, they should all be using capital C's because what they're actually using are kilocalories. So what we consider as a dietary calorie is really a kilocalorie. So let me just give you an idea of how that works. Let's say your favorite food is, I don't know, 250 calories. Maybe that's your energy bar. So that, oops, and I should have drawn that with a capital C, I apologize. That is a dietary calorie because it is coming from food. Lucky Charms. So it's a dietary calorie because it is coming from food. So I can also say 250 dietary. But we can also say 250 kcals or kilocalories. And in science, we generally use the calorie, not the kilocalories. So in science, 250,000 calories. So when we're talking about calories in science, and I'm going to go ahead and say scientific, we are using the original calorie, so lowercase c. However, when food industry talks about it, they are using capital C. And I know you're thinking that's horrible, that's cruel. They told me it was 250 and I thought it was 250 of the original scientific calories. It is actually 250 dietary calories, which makes it 250,000 scientific calories. But that's okay. And the reason it's okay is you've probably read on packages that there are 2,000 calories in an average diet. I should say 200 calories per day. And I know None of us are average. We are all extraordinary. But what that means is that you get to have 2 million scientific calories. So next time you're like, hey, I don't know if I should eat that. It's like 250 calories. You'd be like, no, it'll be fine. I get 2 million calories in my daily allowance. All right. But I do want you to be aware of the difference between the calories that are in food and the calories that we're talking about here. So again, food is all rated as kilocalories, but instead of scaring everybody with that kilocalorie, they just capitalize their C. And in science, we're talking about the lowercase calorie, which is 1/1000th of that. All right. So any questions on anything there? All right. So calorie to joules, definitely want you to know. Also want you to be aware that when a capital C is used, we're intending kilocalories. I'm never going to try to trick you. I'm never going to be like, ha ha, I used a capital C, you're wrong. Again, I'm not going to try to trick you. Where you'll see me use a capital C is when I'm talking about food. So if I'm talking about the calories in food, I will use that capital C, and I'll try to always remember to put in parentheses dietary after it. But again, I'm never going to try to trick you between lowercase and uppercase C, because that's just cruel. So here's that conversion. For every 1 capital C calorie, 1 dietary calorie, there are 1,000 scientific calories. There is a conversion down here on the bottom, just in case you're wondering, because I know if you look at your utility bill, a lot of times they come in kilowatt hours. So there's the conversion between 1 kilowatt hour and joules. We're not going to use it in this class. You might use it in your physics class, or you might use it when you're reading your utility bill. But for us, I want you to know these right here. So any questions on anything here? All right, so here's just some fun facts about calories. So calories versus calories. So here is what we call that grande skinny vanilla latte. And they are saying it is 130 dietary calories. So if it is 130 dietary calories, it is 130,000 scientific calories. So there's a good reason they do not want to use scientific calories on their label. If they called it a skinny latte, and then when you read the nutrition facts, it said 130 calories, you'd be terrified. You're like, oh my God, I'm not drinking that. That's not a skinny latte. So again, there's a good reason that they want to use that capital C, and they don't want to use kilo, because then people think, oh, kilos are heavy. So there's a good reason they've done that. But if it helps whenever you're at the gym and you're on an exercise machine, or if you have one of these smart watches that tell you your calories, they're also talking in dietary calories, not the scientific calories. So it would be horrible if your treadmill talked in scientific calories and then your candy bar was in dietary calories. Those are all on the same system. But we are going to focus again just on our scientific calories and less foods involved. Okay, so questions about anything so far? All right, so next up, types of energy. So 2 main types of energy we're going to look at are kinetic and potential. So potential is energy that's stored, and kinetic energy is the energy of motion. So I kind of like this picture, because up on the top, you see all that water, and it doesn't look like it's doing anything. It looks like it has no energy, but it actually has a lot of energy. And that energy is released when it falls through the dam. Now, normally if we were in class, I could do this with an eraser, but I'm going to go ahead and do it with my calculator lid. So here's my calculator lid, and those of you who've taken physics know that the energy is increased as I raise it higher, and that is because of the force of gravity. And so that energy that's increased is potential energy. So if I drop it from up here, it's going to fall down and release more energy than if I drop it from here. But either way, this position has potential energy. It has the potential to fall and potentially break. I'm not going to drop it because it just might break on me. I do it in class usually with an eraser, and I don't have to worry about the eraser breaking. But again, if it is just right up here and I'm just holding it, that is potential energy. If I were to let it fall, it is kinetic energy. So it is kinetic energy as it's falling. Potential energy, well, I'm just holding it here at this nice height where it could potentially fall and release its energy. So questions on the difference between the potential and the kinetic energy? All right, so our chemical bonds all have potential energy in them. And that is evidenced by our dear friend before he met his untimely death, our gummy bear friend. So what we saw way back when on that first day is that when the gummy bear interacted with that molten potassium chlorate, that heat that we saw, and we did see some sparks flying and some smoke indicating heat. We saw light coming off. All of that was energy being released. That was all kinetic energy. But right now, just relaxing in his little recliner, having a drink, right now, that gummy bear has a lot of potential energy. When you look at a candy bar, whatever it is you're going to eat, you look at those calories are potential energy. They can become kinetic energy once you digest them. Your body can use them as fuel, and as it's using them, they are kinetic energy. But while they're in their package, before you've eaten them, they are then potential energy. So again, our chemical bonds have potential energy. In our exothermic reactions, some of that potential energy is released into kinetic energy. So when sucrose was reacted with the molten potassium chlorate, that was our gummy bear experiment on the first day, the energy released was in the form of kinetic energy. And just in case you were like, hey, that's such a great video, I'd like to see the gummy bear torture chamber again. You don't even have to Google it, it is right here. All right, questions on anything there about that idea that the chemical bonds have potential energy, and in our exothermic reactions, we can release it as kinetic energy? Just imagine next time when you're eating your Lucky Charms or your gummy bear or even your apple, you're like, hey, apple, I'm going to release your kinetic energy. All right, so our first law of thermodynamics is the conservation of energy. So energy is not created or destroyed, it's just converted from one form to another. So in other words, the total amount of energy is always the same. So what's going on in this test tube, and this was taken directly from that gummy bear video, is that the energy, the potential energy that was in the gummy bear is now being released. And we see that steam up at the top. So some of it is going off in heat, and it's a little hard to see, but there was light coming off. We can release energy in the form of light, but all of the energy must be released into some other form. But it never goes away. You can never lose energy or gain energy in the universe. We just exchange energy. All right, so questions on anything here? And thank you, Tasso, for laughing at my bad joke. All right, so again, that first law of thermodynamics, total amount of energy is always conserved. So delta E is going to be our change in energy. Remember, anytime we have a triangle, that means change. Down here we say the E of the system equals the negative E of the surroundings. So for a chemical reaction, the system is right here. So it is your beaker, it is your test tube, it is whatever you have your chemical reaction taking place in. Now your surroundings, they're not just underneath, they're all the way around that beaker. In practice, it is going to be the immediate vicinity, the immediate area of your chemical reaction where we're going to see the change in energy. So if you've got something going on in your beaker, somebody over in, let's imagine we're in lab, 2 labs over, they're not going to feel any effect of your reaction unless you blow something up, in which case they just might. Just for a quick example, I used to do a demo, which we're not allowed to do anymore, but we combine oxygen and hydrogen gas. We add a little spark, and it actually creates an explosion to the extent that people can literally feel something like pushed against their chest and kind of pushes them back. And when I used to do it, I would have to warn everybody in the building because there would be this force that pretty much everybody in the building would feel, and people got really scared. And there were a couple times where people called the police and said they thought a bomb had gone off. So no more of that demo. But unless you have a very explosive reaction like that, again, your surroundings are just the immediate area around your chemical reaction. But if you're going to blow up oxygen and nitrogen together, warn the building and maybe the building next door, just in case they feel that, because it really does rock your whole body back just a little bit. All right. So what we're saying is that the change in energy for the system, must equal the change in energy for the surroundings. So the value of energy, let's say energy lost by the system, is then going to be gained by the surroundings, or vice versa. So it's always the same amount of energy, it's just one of them is losing, the other one is gaining. And I'm going to talk to you more about that. But any questions about that idea that it will be the same quantity, it's just one of them will be losing that energy and the other one will be taking it in. All right. So, oops. You know what? I thought I had another PowerPoint on that, so I'm going to go ahead and create another PowerPoint. I think it does come up later, but I think it'd be good to talk about it now. All right. All right, so what I want to talk about is the idea of an exothermic reaction, and I know we haven't officially titled that yet, but I think it's going to help us to understand what's going on here. So if I say it is exothermic, what I'm saying is that energy is released, often released in the form of heat. So now what I'm going to say is energy lost by the system equals the energy gained by the system is equal to the energy gained by the surroundings. So the same quantity, so if you lose 2 joules of energy from the system, you're going to gain 2 joules in the surrounding. So again, same quantity, just different signs, and that is why we have this negative over here on the right. It's just showing that they have different signs but the same quantity. So any questions on anything there? All right, so calorimetry. So you would have had this super fun experiment on calorimetry. I know you probably have heard by your parents, hey, you can never watch a pot of water boil. That would be so boring. You never want to watch it boil. Well, you would have watched your water slowly decrease. It would have taken about 2 hours for it to slowly decrease in temperature after heating. So this is actually one of those experiments most students don't particularly enjoy, or they really enjoy talking with their lab partner, but they don't particularly enjoy the experiment because you just have to go so slowly to get these temperatures as your water slowly cools. So anyway, so it's not a bad thing that we didn't get a chance to do this experiment, but I believe one of the instructors has recorded it for us, so I will try to find that video for us. So anyhow, calorimetry, we're going to use the equation Q equals MC delta T. I like to remember this as Q equals MCAT. Even before I was a cat person, I used to be a dog person, I converted. Even before that, I like this because a lot of you are pre-meds, you're going on to take the MCAT. Also, this little triangle here sort of reminds me of an A. So for me, it's easier to remember it as Q equals MCAT. This is something I want you to know. And here, the C is a specific heat capacity. And so the amount of energy or heat needed to raise 1 gram of the substance by 1 degree Celsius, it can either be in calories or it can be in joules. So these are published values. Every substance has its own published value for C. M will be our mass in grams, and delta T will be our change in temperature. I do want you to know the specific heat capacity for liquid water, and that is 1 calorie per gram times degree Celsius, or 4.184 joules per gram times degree Celsius. So I do want you to know this right here. All right, so questions on anything here? All right, so this is a typical calorimetry experiment where the system is right inside here. Now the system could be a lot of different things. It could be a hot piece of metal that was put into the water, could be a chemical reaction. At the end of this chapter, you're going to see something called bomb calorimetry, where we do ignite an organic compound. We have essentially a little bomb in there. So it could be many things. And outside here we have water. And the idea is any heat that is lost by the system is going to be gained by the water. But because this is an insulated box, it's going to be stopped by the walls of this box. So if we were to measure the change in temperature for the water, we could figure out how much energy was lost or it could be gained by the system. And it would be gained if, this arrow was going the opposite way, if the system was actually taking in energy. Although it's much easier to calculate it when it is giving off that energy. But again, the idea is you have a system. Again, it could be a hot piece of metal, could be an acid-base reaction, or it could be a little tiny bomb where you're actually igniting something, and we're measuring the temperature change of the water, and then we're using it to calculate the energy change of that system. So we have super high-tech calorimeters we use for this lab. Just kidding. We have coffee cup calorimeters. So they are styrofoam cups, and because we love you so much and because we decided to splurge on you guys, we would have given everybody 2 coffee cups. Yes, 2 styrofoam cups. One would be layered inside of the other one, and that would just give you an extra layer of insulation. We do that because we love you. You're worth the extra coffee cup. We also give you a double layer of aluminum foil for your lid. Anyways. So that's what calorimetry is, and that's what you would have done in your calorimetry experiment. All right, so here it says how much heat is required to raise the temperature of 5 grams of our copper from 25.3 degrees Celsius to 28.5 degrees Celsius. And I should add, that's actually standard. Long Beach isn't being cheap by doing coffee cup calorimetry. When I was a graduate student at Notre Dame, where they had lots of very expensive equipment, the general chemistry students still did coffee cup calorimetry. It still works okay, and it's just a good use of resources to not buy a super expensive calorimeter. Okay, so here it says how much heat was required to raise the temperature of 5 grams of copper from 25.3 degrees Celsius to 28.5 degrees Celsius. And here is the known specific heat for copper. So we're going to plug it in here. Oops. And let me write out those variables. So M is mass in grams. C is going to be our specific heat. Delta T is the change in temperature. And I know this is going to be really hard to hear right after we got through our gas laws chapter. It is in degrees Celsius. Now you could calculate it out into Kelvin, but when people do it in Kelvin, I find that there's a lot of mistakes that get made. So I'm going to encourage you to use Celsius, and I know that's so hard to hear after how hard I was on you in the last chapter about Kelvin. But Kelvin for gases, and we're going to use Celsius for our calorimetry. If you ever forget, just look at the units of your C. They are right over here. For your specific heat, there's your Celsius. All right, so we're using our Q equals MCAT. where Q is our heat, and I should have added that here. Q is the heat, and that is usually the heat in joules. So we are going to find our heat. We're going to start off with our mass. Mass is 5 grams times specific heat, which is 0.385. Oops. Too excited about writing the units there. 0.385 joules divided by grams times degrees Celsius times our change in temperature. And we need to talk about that change in temperature a little bit more. So the change in temperature is always going to be T final, or the final temperature, minus T initial, the initial temperature. All right, so let's grab those. So T final is 28.5, and T initial will be 25.3. The reason I know those is because it says it's from 25.3, therefore that's the initial. I'm going to call that T initial. And then it's going to 28.5, and so this will be T final. So 28.5, and I'm going to subtract out 25.3. All right, so any questions on how we wrote out our equation? All right, go ahead and take a moment and find how much heat was needed to raise the temperature of this copper. All right, so I see Tasso saying 6.16. It looks like Andrew got a similar answer. Anybody else get similar or different answers? Yep, it looks like Maria got a similar answer. And Angie got one similar. All right, go ahead and click in if you would like more time or you are ready to go over it. And I hear a question about sig figs. Let's go ahead and go over those sig figs together. All right, so it looks like about a couple more people need some time, so let's go ahead and take one more minute. Oops. All right, so let's go ahead and give this a try. And I see a sig fig question in the chat, so let's go ahead and write all this out. So we got 5 times 0.385 joules divided by grams times degrees Celsius. And then when we do our subtraction, 28.5 minus 25.3, it looks like we have 3.2 degrees Celsius. And the reason we have 3.2 is because we're looking at digits after the decimal. 1 digit after the decimal, 1 digit after the decimal, and 1 digit after the decimal. So yes, in answer to the question on the chat, it should be 6.2 joules, like so, because we are in 2 sig figs. From that 3.2 degrees Celsius. So any questions on how we calculated this or anything else with the calorimetry problem? All right, so any questions on anything that we talked about today? Okay, let's go ahead and take a break before we start talking about lab stuff. Do you guys want to take a 10-minute break or a 15-minute break? Lab, I'm probably only going to talk to you about it for about 20 or 30 minutes. Do you want to do 10 or 15? All right, so it seems like lots of 10s are rolling in. All right. All right, so let's go ahead and take a 10-minute break, and let's come back at 8:05. And I will be right back.